Todd Parson from the Sorbonne University. So I've actually loaded these sessions with all my sort of for friends, I guess. So I've known Todd for ages as well. As I mentioned at the start of the tutorial, for 17 years since we were working together in Toronto. And Todd is like a genuine probability theorist. And he's actually going to talk about something that isn't microbial communities today. It's going to be epidemiology, but in the context of what we've all experienced. I think it will be super interesting. All right. Yeah, and I also think some of the methods that Todd is going to talk about will be relevant to microbial communities. Stochastic modeling. Yeah, thanks, Todd.
Yeah, thanks, Chris. And and now for something completely different. Though, to be honest, as Chris said, in some ways, the models I'm talking about, I'm looking at host pathogen systems, but the modeling techniques can be used quite generally. This really kind of came about as me trying to do stochastic multitrophic models a number of years ago that led into questions of looking at predator-prey systems or host pathogen systems. And if you want to put this right in the context of what you're doing, think of this as bacteria and bacteriophage, even though I'm really thinking about people and viruses that we get in people. So the title again is The Puzzling Persistence of Pathogens, and it's got to do, let's jump right into the material here, is a question that was really timely when we were thinking about it in 2019, which was 100 years after the H1N1 pandemic. We got interested in some of the questions about why were there 3 waves in the pandemic, and then kind of put all this on the back burner because we had another once-in-a-century pandemic that hit. But I think the question is probably even more relevant today than it was when we started thinking about it. And what I will say, so finally got it nearly finished. I'd hoped to have it submitted before I arrived today, but I didn't, so please be discreet. This is unpublished work. And the question we got interested in is, why is it that you see 1 wave or 2 waves or multiple waves of a pandemic? This is SARS, the original gangster, appeared in 2002, and so it hit many places, including Toronto, quite badly, but basically had a single epidemic wave and then largely disappeared throughout most of the population. The H1N1 pandemic in 1918 had 3 waves, one after the other, sort of this herald wave, the main wave and the secondary wave, and then essentially disappeared into seasonal influenza. Whereas the textbook example of recurring epidemics is, this is pre-vaccination data and probably a preview of the future around measles with the rate we're going with vaccination, which is where we used to have these sort of regular waves of epidemics of measles, which eventually disappeared in the 1950s with vaccination. And so the question we kind of got talking about and are still working on, is sort of the first volley in that direction, is can we predict the probability that you'll just simply have 1 wave, 1 epidemic, and then the pathogen disappears? God, is this ever going to be over? So the way we did is we went right back to ground zero and the textbook model of recurring epidemics. So I assume probably all of you have seen this at some point in your education, but just to remind you, this is the SIR epidemic model, S for susceptible, I for infected, R for removed or recovered. Originally goes back to Kermack and McKendrick in a beautiful paper in 1927. And the way it's sort of standard compartmental models that we use in epidemic theory is you have your population, which is divided into classes. Those who have no immunity, so who can be infected, those who are currently infected and infectious. And then we have sort of removal, where you've acquired some kind of, we're thinking about acute immunizing infections, so you've got immunity and have been removed from the process. If you simply model that without host demography, then it's pretty clear that everything has to end because you just run out of susceptibles, story is over. And so when we think about persistence of pathogens, what we often do is put in host demography. So we assume that there's death or migration, which removes people from the system, and then immigration and birth, which brings people into the system. Fix some notation. So throughout, I'm going to talk about mu as being my birth rate, or immigration rate is bringing in, and we basically balanced birth and immigration in order to keep the system size fixed. Beta is this transmission rate. So we're thinking about mass action transmission. A susceptible encounters an infected individual. These events happen at rate beta, and that leads to transmission. And again, gamma is a recovery rate, so it's the removal. So there's a certain amount of time. This is a Markov model, so the exponentially distributed, at which point you remove from you recover from the infection and you're no longer infectious. So now, what we usually do with this is we move to an ODE formulation. And this is sort of, and actually sort of a parenthetical comment is that although that 27 paper is kind of remarkable because it gets cited thousands and thousands of times for these equations, but actually they were much more prescient, and they actually spent a lot of time talking about stochastic models in that early work. So I think we're all sort of used to these equations here. Basically, I've just taken and translated into differential equations describing not the absolute number of individuals, but the density relative to the total population size. And we see sort of inflow of susceptibles, mass action term of sort of contact and removal, death. We have this mass action moves you from the susceptible class into the infective class. Any of the death or recovery removes you from the infective class. And finally, you're moved into the recovered class. I don't think I need to sort of spend a lot of time talking about this, though I will sort of show you the pictures that we always show afterwards in just a second. I want to think about this same model, the same box plot, not as describing a system of differential equations, but as describing a Markov chain. And so what I mean by that is I have the same transitions. You're going from susceptible to infected, infected to removed. Only now I think of those rates not as being a flow of mass, but rather a flow of probability. So my rates are interpreted as probability per unit time of these events happening. This leads me to a Markov chain, a discrete Markov chain with, again, finite states. And I have transitions, basically the susceptibles can go up and down by one, infected, sort of through death or recovery, sort of immigration or death, and then sort of these infection process here and recovery process. For those of you who attended my tutorial, I talked a bit about master equations. You can write down the master equation here. You can't solve the master equation. It's kind of not really that helpful. But the one thing I do want to point out, which is going to be very helpful, is the relationship between this Markov chain and the ODEs that I just showed you. And that's what's called, if you're a mathematician, it's called the Kurtz law of large numbers. If you're a physicist, it's the Van Kampen expansion. And the point is you can understand these equations as a limiting case of this stochastic model in a very clear fashion. And what ends up happening is it turns out that the parameter n here, which is sort of the population size, we take n to infinity while rescaling, going from absolute numbers of individuals to densities of individuals, and we get the ODEs that we're sort of used to from first year calculus. And the reason I want to mention this is because it's going to come up in what I want to think about this, is this macroscopic approximation is useful most of the time, and then when it's not useful, sort of when actually the interesting probability happens. Before I get into the probability theory, just two last comments, and sort of, again, hopefully you've all seen this before, but I just want to remind you, is that the key number in all of these models of dealing with epidemics is what's called the basic reproduction ratio. It goes back right to the work of Kermack and McKendrick. And so we always call it R0. Hear a lot about that these days. R0 is bigger than 1, R0 is less than 1. And again, it's the product of the transmission rate times, this is 1 over the rate, gives me the expected duration of an infectious period, times the multiple of the population that's susceptible, and the 0 in the R0 comes the fact that we're always going to talk about the initial population susceptible. And the product of these three quantities gives me my R0. It's the number of new infections caused on average if I were to take a single infected individual and put them into an epidemiologically naive population. Right, so if I just kind of repeated that experiment a bunch of times, on average, the first infected person would produce R0 more infections. R0 is a bifurcation parameter in the system of ODEs. When R0 is bigger than 1, you have exponential decay in the number of infected. When R0 is bigger than 1, you have exponential growth. And because of this model that I have has got demography in it, the whole thing eventually settles down to an endemic equilibrium, a stable state for those ODEs. And what's happening is you get 1 over R0 gives you the fraction of the population that remains susceptible, that sort of is susceptible in the stationary state. And Y star is the fraction that remains infected. And you sort of settle down to this sort of fixed level of infection, which is 1 minus 1 on R0, multiplied by this second parameter, which is going to be important, epsilon. And what epsilon is doing is it's measuring the mean infectious period as a fraction of host lifespan. Okay, so we're moving sort of from units of time, we're measuring times in terms of lifespans and sort of asking what fraction of a lifespan is your infectious period. So, just to remind you again of this story, so these are, if I were to run and simulate those ODEs, I'd get a picture like this. Shown it here, basically blow up on the number of infected in the log scale in order to actually see what's happening. But the important thing is we see this series of oscillations, damped oscillations that lead to the steady state. And this is again sort of the original model that was proposed, the textbook model for persistence of infections leading to these sort of recurrent cycles. Just showing you here on this side, sort of the same picture in phase space and the same picture in log phase space. Now, overlaid on top of this, and I hope they're visible, are stochastic simulations using the Gillespie algorithm of the same stochastic process. And you can see that, they're not very visible here, but there's a bunch of like wiggly lines kind of floating around these bright red OD lines. And that's giving me my individual realizations of the stochastic process that gives me these ODs. Now, what is important to me, and some language that I want to fix, what I want to talk about, is stochasticity sort of hits this system almost entirely down here in the bottom, what I'm going to call the trough. And what I've done is this yellow region basically is running through, giving you, this is that equilibrium fraction infected, and everything below that I'm going to call the trough. Everything above that I'm going to call the epidemic phase. Right? So this phase of exponential growth, and then it crashes down. You arrive back at the trough. We are down in the situation where you're now below the endemic equilibrium. And what you can see is we're down there, there's a few different things that can happen. So in dark here, I've got this example of one example run we did where there was never even an epidemic. They were just kind of like, we introduced a single infected individual into our population and didn't really go anywhere. It infected a few people and then it fizzled out. That's what I'm going to call fizzle throughout the rest of my talk, because that's when you don't get all the way to even starting an epidemic. Second scenario that can happen is the pathogen managed to get all the way and cause an epidemic, but then it kind of comes through and it hits the end of the first epidemic. And remember what's happening in the first epidemic is it's driven the fraction susceptible down quite a bit. So it's kind of exhausted its resources. And while the OD is guaranteed 100% of the time to go back up, the stochastic process doesn't do that. It can sometimes burn out. Basically, we end up running out of this sort of, we run out of susceptibles. They're not completely exhausted, but there's a lot fewer of them, and the virus is just not able to keep up with enough infection in order to keep going, and it burns out. And then the final scenario, which is in the unfortunately not terribly visible trajectories on these things, is sometimes it just manages to keep going and it persists and carries on to start a second epidemic and keeps on going its merry way. And so the first question we want to ask ourselves is, could we predict the probability of burnout in these systems? Those who went to my tutorial, I said simple is beautiful, and so what I want to start with is, like, again, sort of about the simplest possible model that I could apply to the system, which turns out to be quite adequate to the task at hand. And the model is a birth and death process, like I talked about the other day. Simple model. Basically, individuals either give birth at a certain rate or they die at a certain rate. Now, in this case, birth and death is not actual birth and death. It's the birth of a new infection, so an infection event becomes a birth. And a recovery or a death is like an actual death or a recovery are both counted as death in my birth and death model, because it's taking one person out of the infected state and out of the epidemic action. Now, why it turns out that I only need to do anything more than this, remember what I said, all the action stochastically kind of happened down here at the very bottom where there were very few infected individuals. And it turns out that when I'm down there, in this state where it's rare when the stochastic action happens, the number of susceptible individuals is almost entirely independent of the infection. There's just simply not enough infections to have any real effect on the number of susceptibles, because there's just so many more susceptibles. And so the infection events are a drop in the bucket, and they kind of are negligible from a mathematical point of view. And so what I can do is I can say, okay, I don't want to try and deal with a three-dimensional stochastic system, because like anything more than one dimension, you probably can't do anything with your stochastic system. But what I can do is say, well, I'm just going to replace the susceptible. I'm just going to ignore the effect of infection altogether on the density of the number of susceptible individuals. And that just about the simplest ODE I could ask for, I can solve it in one line. Now, the stochastic model said the rate of infections per infectious person was the number susceptible divided by population size. So this is, again, per infected. S on n is approximately x. That's what I said, is x is the density of S. And I'm going to approximate it not by a stochastic quantity, but by this ODE right here. And so what's happening is I have actually taken this rather complex stochastic system and turned it into one ODE and one birth and death process, which are about the two simplest things that you can possibly deal with if you're doing this kind of mathematics. And what's really nice about this is a very classical paper by Kendall in 1948, where he actually completely analyzed birth and death processes if you allowed time dependence in the rates. And the crucial thing here being is that because I'm approximating the number susceptible, which is in real life is stochastic, but I'm approximating by a deterministic quantity, I can just plug that in as being just a time-dependent rate. And I did that. And this is the last of my equations, I promise. But I mean, sort of actually, well, first of all, we didn't come up with this. It's a very old result from the 1950s where Bartlett showed, using the same kind of birth and death argument, so the probability of fizzle was 1 on R. Remember, that was the probability that it never started an epidemic. Our contribution in this work is that we were able to analytically characterize the probability of burnout in the system. If I had a lot more time, I would actually try and walk you through what every aspect of this means, but let's sort of say that the crucial thing is that sort of we've got this expression and we see that it depends on the fraction. This, remember, sort of this y star that I wrote was the equilibrium density, but that's also where I define my trough. And what we want to ask basically is that sort of, I'm asking sort of how, this is sort of n y star is approximately the number of individuals who are infected when you enter the trough. X in is the fraction susceptible when you enter the trough. And then I can just basically integrate that whole branching process that I showed you. Bit of working, we can get an exact expression for the entry point of the trough. So if you persist, that means you didn't burn out and you didn't fizzle. So we can basically just take these two simple expressions that we got from a branching process and compute the probability of persistence. That might seem like a way too simple an approximation to actually work, but here you can see the same plots on the log and linear scales of comparing that to simulations. The solid curves here are the analytical results. The gray over top of that is a simulation. You can't even see the difference at all if you're on the linear scale. You have to work on the log scale. You'll notice that our simulations start to look really bad here. And it turns out that some of these events are so low probability that we actually had to run computer simulations for weeks in order to even compute the probability of these events. So like analytics win, because like, a couple seconds to plot these things in sort of Maple or MATLAB versus running your computer for weeks and weeks to simulate something which turns out to not be a very good. You approximate it really well, except when your simulations aren't good enough to compare to. Now, what's interesting we learned from this is a few things. I mean, one of them is you notice there's an interesting bimodality, which we weren't really expecting when we first did this work. We've all been talking, we've heard so much about let's bring the R below 1. And that's absolutely what we should be aiming to do at all times. But what's interesting, and everyone sort of assumes tacitly that the bigger the R is, the more likely the pathogen is to persist. And what we've actually found out is that that's not the case. It's actually a bimodality. How much time do I have, Chris? Okay, cool. And so what you're seeing is that sort of there's two different strategies. There's what I would call a low R strategy and a high R strategy. Now, let's actually sort of unpack what that might mean. So if your R is really low, you're not very good at transmission. But because you're not very good at transmission, you're not very good at bringing down the number of susceptibles in the population. You're basically not very good at running out your own resource. And so therefore, a low infection strategy is able to maintain resources that gives it a fighting chance to come back for round 2. The high R strategy, over here, is you just infect everything in sight. And although you're kind of just driving down the susceptibles, if you are fast enough, you can infect every person who comes through that door and keep going. And it turns out that sort of the sweet spot for the virus is, the sweet spot for us, but not for the virus, is either below 1, let's just keep this thing just going down, or there's a second point between 2 and 3, where viruses are just good enough at transmitting that they knock out their own environment and sort of wipe themselves out. And what's nice is when you have an exact analytical expression, we can actually compute that function. The other thing it turns out, if you look at that expression and you can just compute the derivatives, you can say that that probability of burnout, of persistence, is an increasing function of epsilon, which was the infectious period. So it sort of seems that there's sort of now, we always think about sort of this one-dimensional thinking about fitness, where sort of you're always trying to maximize your fitness. Well, it turns out that that's not quite what's happening in epidemic systems. You either want to have this low R strategy or this high R strategy, a low fitness strategy, a high fitness strategy. But then there's this third aspect, and it's like a life history strategy aspect, which says that if I can hang out longer in each host, whether by being a milder infection, by sort of becoming sort of, and this might be an explanation, and might be, I'm not going to say for this perceived idea of evolution toward reduced virulence, but this idea that if I can stay around long in a host, I can wait out the bad times, and that also sort of becomes sort of a second dimension of strategy that's available to viruses. Now, the reason I said this was sort of a puzzle in my title is that all this is, like, I hope I've told you a great story. There's only one real problem, is that when we compare it to data, what we've actually plotted here is using our expressions, is the basic reproduction ratio on the log scale here, this lifespan, infectious lifespan on the x-axis, is what you see is that every human pathogen that is persistent has about an infinitesimal probability of surviving. So what does this say? I mean, this is our textbook model. We need to update our textbooks because these are great ODEs that say, yeah, population, viruses persist and you have these recurring damn cycles, except that when you actually take a bit of time and look at this as a stochastic process, in fact, nothing survives. What is cool, though, is that the story that I told you is still on this slide, and we think that this sort of simplified story, it can't actually explain any real persistence of anything, but it does get the qualitative behavior right, which is you have one cluster down here of low R, of things that have been around for a very long time, influenza, Ebola, pneumonic plague. You have another cluster here of our old friends, measles, pertussis, mumps, chickenpox, which are very high R's, and they've been hanging around for a long time. The only person we really have in this dead zone between 2 and 3 is SARS-CoV-2, but SARS-CoV-2 didn't stay there. It evolved. It left that. You have the Delta variant, which raised its R to about 8, and the Omicron variant has an R somewhere around here around measles. So it's interesting, although we're not predicting even remotely correctly the probability of these things surviving, we're getting the qualitative fact of this division correctly. There's two strategies. And when I talked about a lifespan strategy, over here, we've got something which spends a very long time in the host infectious, which is HIV. And it's all able to survive in what should be the dead zone, basically by being able to just simply stay in a host that long. So thanks everybody for the opportunity to speak today. Hope this was interesting, even though it had nothing to do or very little to do with microbial community ecology. And I want to thank these are my collaborators on this project, Ben Bolker, Jonathan Dushoff, and David Earn. And Jonathan and David and Ben are actually really doing stuff with epidemiology, which is why this has taken so long, is because they've actually been like going out and trying to save people while I've been doing theoretical nonsense. So thanks very much for your time.
A little over time, but we'll do one question if anybody's got something that's. I mean, oh, okay. Go ahead.
So, if you calculate these burnout probabilities and determine what extent does it actually correspond to fitness between two variants of the virus? So, if you had like your low R0 virus and another one that was higher R0, does this actually tell you which one would outcompete the other?
So in this case, this work is just in one strain. We're just looking at the survival of a single strain. However, if I can sort of plug my own work, Parsons et al. 2018 interface, Day et al. 2020, Proc Royal Society B, and there's a third paper which is Gandon et al., which is on the medRxiv for a few months now, and they're basically all dealing with the two-strain versions of this kind of analysis. And what we actually are seeing is the same kind of thing that I'm talking about. This life history strategies really do matter. And what can turn out is they're sort of in both extremes. You can look at things in the weak selection regime, and you see a clear signal in favor of reduced virulence over certain time scales, which then can be we looked in an adaptive dynamics framework to show that sort of creates, there isn't a long-term evolution toward reduced virulence, but there is a station distribution in which you have more time relatively spent in reduced virulence. but can still have. And then the work on the Met Archive actually talks very specifically about looking at multiple strains and the possibility of strains surviving the end of an epidemic phase and how the life history strategy affects that.
Okay, let's thank Todd again. Now we have Jimmy Gonzalez Nunez from Johns Hopkins, who's also going to be talking about stochastic processes and quench noise.